Good day and welcome back. Lecture 4-3 is on the frequency response design by using pole and zero placement. The objectives are to describe the advantages and disadvantages of designing a control system using pole and zero placement. To also use pole and or zero placement to improve the transient and steady state response of a control system by satisfying certain design specifications, and to compare the root locus, step response, and ramp response for a compensated and uncompensated system to confirm that the design constraints are satisfied. At times in the design of a control system, it is better to place the poles and zeros of the closed loop control system to obtain certain steady state and transient characteristics. The following theory is used to place the desired zeros and poles. Assume the closed loop transfer function T of S and the plant GP of S are given by the following. T of S is equal to the numerator of T of S divided by the denominator of T of S, and we've also seen that it's equal to GCGP divided by 1 plus GCGP, and you can write this in terms of the numerator and denominators as NCNP over DCDP plus NCNP. And you can also write it in terms of the polynomials in descending order as shown in that last term. So assume that GP of S is equal to NP of S over DP of S. So using these equations, the compensator and open loop transfer function for the desired poles and zeros is given by the following formula by using algebra. So GC of S is equal to T of S over GP times 1 minus T of S, or in terms of the numerator and denominator, NT of S, dP of S, divided by NP of S times the quantity, dt of S minus NT of S. Or finally, GCGP is equal to T of S over 1 minus T of S. The advantage in using this technique is that the poles and zeros can be placed exactly at the desired locations. The disadvantage is the same as for most designs. It uses the plant model, so if there is any error in the plant model, the compensator may not yield the desired results. Finally, use the relationships in Table 1 to get the desired system type number. We have talked about system type number before, but if you want a type 1 system, then A naught should equal B naught. Or if you want a type 2 system, A naught equals B naught and A1 equals B1. Or if you want a type 3 system, A naught equals B naught, A1 equals B1, and A2 equals B2. In class activity 1, for a control system with a plant GP of S equal 1 over S plus 1 times S plus 2, design a controller to place the poles at -3 and -4 with a zero steady state error due to a step input. Now the zero steady state error due to a step input tells us that we have a type 1 system, which means that A naught equals B naught. So our closed loop transfer function is T of S is equal to B naught over S plus 3 times S plus 4. This is our desired closed loop transfer function, which is B naught over S squared plus 7S plus 12. And note that A naught is 12. So, since A naught must equal B naught, the desired closed loop transfer function is 12 over S squared plus 7S plus 12, which is the numerator of T of S over the denominator of T of S. The numerator of the plant is given in the problem statement, and that's 1. And the denominator of the plant, also given in the problem statement, is S squared plus 3S plus 2. So the desired controller, GC of S, is given by the equation NT dP, we're going to drop the S's for brevity, over NP times the quantity dt minus NT. So this equals 12 times the quantity S squared plus 3S plus 2 divided by NP, which is 1, times dt S squared plus 7S plus 12 minus NT, which is also 12. And this simplifies to 12 times S plus 2 times S plus 1 divided by S times S plus 7. And finally, K, GC of S, GP of S is equal to 12K over S times S plus 7. So now let's take a look at the root locus before and after the compensator, and look at the step response before and after the compensator. And recall that if I calculate T of S, which I will need for the step response, it would be 12 over S squared plus 7S divided by 1 plus 12 over S squared plus 7S, which equals 12 over S squared plus 7S plus 12, which check is indeed our desired closed loop transfer function. Okay, here's the MATLAB plot of the root locus. So the uncompensated system, we were indeed at -1 and -2. And afterwards, with a gain K equal to 1, we do indeed have poles at -3 and -4. And now we need to go to the step response in order to see that the zero steady state error. Okay, here's the plant before and after compensation. And what you should notice here is that originally there was a large steady state error larger than 0.65, and that the settling time was around 3 seconds or so. And after compensation, the steady state error is now 0, and the system settles in about 2 seconds. So there was an improvement by placing the poles at -3 and -4.